Hello, everyone, and welcome to today's lecture. Today, we'll talk about something I find very exciting: agentic workflows, or autonomous AI systems. This is something that is truly changing how we think about artificial intelligence and automation. So get comfortable, and let's dive into this fascinating topic. Let me start with some context. Artificial intelligence has come a long way in recent years. We've gone from systems that could only answer questions to systems that can actually execute complex tasks. But what happens when AI systems don't just follow instructions, but can actually plan, make their own decisions, and solve problems completely independently? This is where agentic workflows come into play. It's a new generation of AI solutions where the system works more like an autonomous agent, an independent collaborator, rather than as a passive tool. Instead of just reacting to commands, these systems can take ownership of entire problem-solving processes, from planning all the way to execution and quality control. During this lecture, we'll explore how agentic workflows work, what possibilities they create, and not least, what challenges they bring. Okay, so let me start with a scenario I'm sure many of you recognize. Imagine you open ChatGPT and ask it to write a report about the market situation in your industry. You get back a response in about 30 seconds. Fast and smooth. But when you start reading the result, you realize there are problems. Some claims are outdated. Important competitors are missing from the analysis. Sources aren't verified. And the conclusions feel a bit too generic and superficial. So what do? Well, you correct the instruction. You ask for a new version. You discover new problems. So you iterate again, and again, and again. And here comes the important question. Why must you be the one who discovers all the errors? Why must you adjust the strategy? Why must you guide each individual iteration? What if the AI system could do all of this itself? That's exactly what agentic workflows are about, giving AI systems the ability to own and drive the entire problem-solving process. So, what exactly are agentic workflows? Simply put, it's about building AI systems that don't just execute tasks, but can actually plan, that is, figure out how the task should be solved, make decisions about which steps are actually needed, evaluate their own results and see if they're good enough, adapt their behavior when something goes wrong, and iterate until the goal is truly achieved. This represents a fundamental shift. We're moving from AI that just reacts to instructions to AI that takes ownership of problems. Let me give you a running example that we'll return to throughout this lecture. Imagine an AI research assistant that gets a task: write a literature review on quantum machine learning. A traditional AI system might just generate text based on its training data. It does its best, but the result is likely incomplete. An agentic system, on the other hand, it plans the work first, then searches for current articles, reads and analyzes them, identifies gaps in coverage, searches for more information, writes the review, evaluates quality, improves the text, and only then delivers a final result. Do you see the difference? This is AI that actually takes responsibility for the entire process. To understand why agentic workflows are so important right now, let me show you how AI has evolved in 3 distinct waves. Wave number 1, from 2020 to 2022, answering questions. This is when ChatGPT was launched. Suddenly, AI could answer questions, generate text, translate languages. Fantastic. But the limitation was that you still had to guide each individual step. Wave number 2, 2023 to 2024, executing tasks. Now AI can write code, analyze data, generate images. We've gone from just answering to actually doing things. But the limitation remains. You still have to validate and correct the results. And now we're in wave number 3, from 2025 onwards, owning problems. We're now over a year into this wave, and we're already seeing concrete results. AI can take a complete problem, plan the solution, execute the work, and ensure quality. During 2025, we saw mass adoption of agentic systems in production. The opportunity here is that you can focus on the goals, while AI handles the actual execution. This is a paradigm shift in how we can work with AI. So why is this so important? Let me give you three main reasons. First, we're moving from seeing AI as a tool to seeing it as a colleague. AI doesn't just become something you use for individual tasks. It becomes something you can actually delegate entire areas of responsibility to. Second, scalability of expertise. Imagine a researcher who can get help from multiple AI assistants working in parallel on different parts of a large project. Or a developer who can let AI agents handle testing, bug fixing, and documentation simultaneously. It creates a completely new level of productivity. Third, new possibilities open up. Problems that were previously too complex or too time-consuming suddenly become solvable. We humans can focus on creativity and strategy, while AI handles the heavy execution. In short, agentic workflows represent the next generation of AI. We're moving from assistants to autonomous problem solvers. Okay, so what characterizes an agentic system? Let me give you 5 core characteristics with concrete examples. Autonomy. That means the ability to make own decisions based on context, without constantly needing to ask for permission. Example, I need more data to answer this. I'll run a database query. Goal-driven. The system works towards an overarching goal, not just following a list of instructions. Example, the goal is a complete overview, so I'll continue searching until all main areas are covered. Adaptability. When circumstances change, the system can adjust its strategy dynamically. Example, first search gave too few results, so I'll broaden the search terms. Iteration. It works in loops where each step informs the next. Example, first draft lacks depth, so I'll search for more specific sources and rewrite. And self-reflection. The system can evaluate its own results and actively improve quality. Example, have I achieved the goal? No, coverage is incomplete. Continuing work. The core of all this is that the agent takes ownership of the entire problem-solving process, not just individual steps. That's the fundamental difference. For a system to be called agentic, it needs 5 fundamental capabilities. Remember these, they're fundamental. 1. Perceive its environment. The system must be able to read and understand the situation. 2. Reason about goals and strategy. It must be able to think about what needs to be done and why. 3. Plan its actions. Break down the problem into concrete steps. 4. Act by actually executing the plan. And 5. Reflect on the result and learn from it. The important thing is that the agent works in a loop. Observe, think, act, evaluate, adjust, and then the cycle starts over. This makes the system more like a problem solver than a script, and that's exactly what we want to achieve. Now I'll give you a really hands-on example to concretize these capabilities. Imagine we have an AI agent that's supposed to fix bugs on GitHub. It gets an issue that says, button crashes the app when clicked twice quickly. Let's walk through how the agent uses the 5 capabilities. Perceive. The agent reads the issue description. It identifies that this is a bug, not a feature request. It notes that the problem involves a button and double-click. Reason. Okay, this sounds like a race condition. I need to first reproduce the bug to understand it, then find where in the code the problem occurs, and finally implement a fix and verify that it works. Plan. The agent creates a step-by-step plan. Step 1, find the button component. Step 2, write a test. Step 3, run the test. And so on, all the way to creating a pull request. Act. Now the agent actually executes the plan. It uses code search to find button.jsx, writes a test, runs it, and yes, it fails, which confirms a bug, identifies the problem, on-click handler lacks protection against multiple clicks, implements fix by disabling the button during processing, uses an is-processing state that prevents new clicks while the first process is running, runs all tests again, they pass now, and creates a pull request. Reflect. Does the fix work? Yes, the test passes. But are there edge cases I missed? What happens with triple click? So the agent writes additional tests to ensure the solution is robust. And the result? The bug is fixed, tested, and ready for code review, completely autonomously, without human involvement. This is the power of agentic workflows. Now, let's talk about how to actually build these systems. There are three main architecture types. Single agent, the simplest. One agent handles everything itself. For example, a coding assistant that writes code, tests it, and fixes bugs on its own. Multi-agent team. Here we divide the work between multiple agents with different roles. Imagine a planner agent that plans a work, a coder agent that writes the code, a reviewer agent that reviews it, and a tester agent that runs the tests. Each agent specializes in what it does best. Hierarchical architecture, the most sophisticated. Here we have a manager agent at the top with specialized capabilities for decomposition and delegation. The manager agent breaks down complex goals into sub-goals, delegates to specialized team agents, monitors progress, and synthesizes results. For example, if we're building an e-commerce platform, manager delegates to back-end team agent, front-end team agent, and DevOps agent. And each team agent can in turn have its own sub-agents. The choice of architecture depends on problem complexity. Simpler tasks? Single agent is enough. Complex projects? Then we need teams or hierarchies. A central capability of agentic systems is planning. And it's not just about breaking down a goal into subtasks. It's about choosing the right strategy. Let me show you how our research agent thinks when planning. The goal is to write a literature review on quantum machine learning. But how should it do it? The agent considers several strategies. Strategy A, broad search. Search broadly. Filter the 50 most cited articles. Read all. Problem? It takes far too long. Strategy B, focus search. First identify main subcategories like algorithms, applications, hardware. Then search 10 to 15 articles per category. Write the review structured by category. This is a selected strategy. It balances coverage and efficiency. Strategy C, survey-based. Find the 2 to 3 latest survey articles and use their references as foundation. Problem? Risk of missing new research directions. So the agent chooses strategy B because it's most optimal. This shows that the agent doesn't just follow instructions. It actively reasons about what's a good strategy for this particular situation. To be truly useful, an agent must be able to act in the world, and that means being able to use external tools and systems. But it's not enough to just be able to use tools. The agent must also be able to determine when a tool should be used, why it should be used, and how the results should be verified. This makes the agent an active actor rather than a passive assistant. Let me give you an example with our research agent. It has access to several tools. Arxiv_search to search for articles. Semantic_scholar_pi for metadata and citations. PDF_reader to read PDFs. Summarizer to summarize long texts. And citation_analyzer to analyze citation networks. The agent's decision process looks like this. I have a question requiring current research. Then it uses Arxiv_search. I need to understand which articles are most influential. Then it uses citation_analyzer. The summary must contain the main results. Then it compares with abstracts and conclusions to verify. And in practice, the tool sequence becomes search articles, analyze citations, read and summarize each article, and then collect everything to write the review. It's this type of intelligent tool use that makes agentic workflows so powerful. When you start building agentic systems, you soon discover that certain architectural patterns recur over and over. It's not about free improvisation. Agentic workflows are about structured autonomy, where freedom combines with clear roles and responsibilities. Let me present 4 established design patterns used in practice. REACT, it stands for reasoning plus acting. The agent alternates between thinking and acting. I need to find articles about X. Search. Results are too broad. Refine search. Better. Now I can continue. Chain of thought. Here the agent breaks down the problem step by step and reasons explicitly. To write the review, I must first 1. Define scope. 2. Identify key concepts. 3. Find sources. 4. Synthesize. Reflection or self-critique. The agent evaluates its own output and iterates. Write draft. This lacks discussion of limitations. Add section. Now it's more balanced. End tool use agent. The agent has access to external tools and determines when they should be used. I can't answer this from my knowledge. Use web_search. Now I have the right information. These patterns are proven and reusable. When you build your own agentic systems, you'll likely use some combination of these. Now we come to something that's relatively new, but extremely important, Model Context Protocol, or MCP. One of the biggest challenges in agentic workflows has been, how should agents connect to external tools and systems? Historically, each AI platform has made its own solution. ChatGPT has its plugins. Claude has its tools. LangChain has its own. The result? Total fragmentation and zero interoperability. Model Context Protocol is an open standard protocol that solves this problem. It defines a unified way for AI agents to interact with tools, data sources, and services. It's developed by Anthropic, but it's open and community-driven, and it's actually starting to gain really good traction now. So how does MCP work technically? It's a client-server protocol. Very simple concept. You have an AI agent that is the MCP client. It communicates via the MCP protocol with an MCP server, and the server in turn connects to the actual external resource. Let me give you an example. An AI agent wants to read files from disk. It connects to a file system MCP server. The server exposes tools like read_file, write_file, list_directory, and the agent can call these tools via the MCP protocol. The nice thing is that the same protocol works regardless of which tool it is. File system, databases, GitHub, web APIs, all the same standardized interface. Okay, so why is MCP so important for agentic workflows? Let me give you 4 main reasons. Interoperability. One MCP server works with all MCP-compatible agents. Claude, GPT, local models, doesn't matter. Write once, use everywhere. Security. You get clear boundaries between agent and tool. You can implement permission systems and access control. And you have the ability for sandboxing dangerous operations. Modularity. You can add or remove tools without changing the agent. You can swap out implementations transparently. And you can reuse the same MCP servers across different projects. Standardization. You get consistent error handling, uniform documentation, and community-driven best practices. This is why MCP is becoming the de facto standard for AI tool integration. Okay, now we've talked a lot about the possibilities, but we must also talk about the risks. The more autonomy we give a system, the greater the risks also become. An agent can make unexpected decisions we haven't foreseen. It can misinterpret goals in ways that lead to problems. And it can use resources in ways we didn't intend. Therefore, it's absolutely critical to combine agentic freedom with constraints, monitoring, and human control. Let me give you some concrete examples of what can go wrong. Here are 4 risk scenarios you need to be aware of, a mix of documented problems and potential risks. Risk number 1, resource consumption without limits. This is a documented problem. Scenario, a research agent gets a task to find all relevant articles. Sounds reasonable, right? But the agent makes 10,000 API calls and costs $500 before anyone can stop it. This has actually happened in production systems. Solution, set budget limits and require approval for large actions. Risk number 2, goal misunderstanding, also called reward hacking. This is a classic thought experiment illustrating a real design challenge. Scenario: an agent should maximize customer satisfaction. What does it do? Gives 90% discount to all customers. Technically, it fulfills the goal. Customers are super satisfied, but the company goes bankrupt. Solution: define multiple constraints and KPIs, not just a single goal. Risk number 3, unexpected side effects. Scenario: a coding agent should optimize performance. What does it do? Removes all error handling because it makes the code faster. Performance? Fantastic, but the program crashes at the slightest error. Solution: require that the agent validates that all existing functionality is maintained. Risk number 4, security risks. Scenario: an agent has access to shell commands. By mistake, it runs rm-rf/ and deletes the entire system, or exposes API keys and log files. Solution: sandboxing, whitelist of allowed commands. Require human in the loop for critical operations. These risks are real, and you must design your systems with them in mind. So how do we handle these risks? Through what we call guardrails. Set budget limits and approval requirements for large actions. Define constraints, not just goals. The system must follow multiple rules simultaneously. Validate that functionality is maintained when changes are made. Use sandboxing and whitelist commands to limit what the agent can do. And implement human in the loop for critical operations. This is about finding the balance between autonomy and control. We want to give the agent freedom to work independently, but within clear boundaries that protect against catastrophic mistakes. Think of it as giving someone the keys to the car, but with certain limitations. You can drive, but not over the speed limit, and certain roads are forbidden. Agentic workflows also raise deeper questions about responsibility and governance. If a system makes decisions on its own, who then bears responsibility for the consequences? If the agent does something wrong, who is liable? The questions we must answer are: who is responsible when an agent makes an autonomous decision? What types of decisions may be made fully autonomously and which require human approval? How do we document the agent's reasoning so we can understand why it did what it did? This means technical solutions must be complemented with policies, clear rules for what is allowed, ethical frameworks, principles the agent must follow, and organizational governance, processes for decision-making and responsibility. These are not just technical questions, they're organizational and even legal questions. And the more we use agentic workflows, the more important it becomes to have good answers to these questions. Let me conclude with 3 fundamental questions we all must reflect on. When is it appropriate to use autonomous systems? Which tasks really suit agentic workflows and which don't? When should humans retain full control? Where is the line between appropriate autonomy and too much risk? And how do we ensure systems work in line with our goals and values? How do we build ethics and responsibility into these systems? These are not just technical questions. They're ethical, legal, and organizational questions. And I'd love to hear your thoughts about this. So now I open for discussion. And with that, we've reached the end of today's lecture on agentic workflows. I hope you've gained a good understanding of what agentic workflows are, how they work, what possibilities they create, and not least, what challenges we must handle. This is an area developing incredibly fast. In a year, much of what I've talked about today will likely be standard, and there will be new exciting developments to talk about. So stay updated. Feel free to experiment yourselves if you have the opportunity, and think critically about where and how these systems should be used. Thank you for your attention.